This exercise is about adding sediment and morphology to a hydrodynamic run. Again, we will start from a schematized rectangular basin, a model, a river model, and we add sediment to that. We analyze the sediment transport, then we add morphology, and we add the effects of the morphology in a 1D fashion and a 2D fashion. The basis for this exercise is again a rectangular basin of about 10 kilometers long, 1 kilometer wide, with at the upstream part a river inflow and at the downstream side a constant water level. I run that model and I'm going to analyze again with you what are the outputs of that model. This is then the water level. This is then the bed level. And you see that there's a horizontal bed level of 5 meters. And at the downstream side, the water level is a 0 at the reference level. And there is flow from the landward side with basically with a water level slope because of the friction. I'm also going to plot the velocities here. I do it in red, a new plot. And this gives the remarkable conditions that since we have a flat bed and we have friction, the inflowing water will flow under a water level gradient. And because there is this water level gradient, it means that the flow will accelerate. And the friction by the bed needs to be counteracted by a water level slope, and that leads to an acceleration of flow. You can simply see this because at the seaward side or at the downstream side, the cross section is smaller than at the upstream side, and because there is the same amount of water needs to go through that, it automatically means that the velocities at a larger cross section upstream are smaller than at the smaller cross section downstream. If we have accelerating flow, that means also that we will have erosion of the bed because the velocities downstream are larger than upstream. It means more sediment will be eroded at the downstream side. So that's what we expect. Let's see if that's true. I'm going to the model 001 and first I'm going to add sediments. That is under processes. I can add sediments. If you press that button, you can add non-cohesive and cohesive sediments. So non-cohesive is sand and cohesive is mud. We choose for this sand option. We have to give the sediment a name before we can add it to the sediments definition. Sediment A, or let's call it sediment sand. And we remove A. Right. Close it. This will automatically change the how the depth is calculated in the more file. If we add sediments, we also have to change the boundaries, and you will see in the upstream boundary here that under transport conditions there is this sediment sand, and we have to can provide a concentration over here. We don't do it because we assume that at the inflow of our model we have equilibrium sand concentrations, and these equilibrium sand concentrations are automatically calculated via Rhine formulations. With a certain velocity there's a certain sediment transport, sediment concentration, and the software Delft3D automatically calculates that concentrations. The physical parameters, we go to morphology, and here you see that the equilibrium sand concentration profile at the inflow boundaries is switched on. So that means that this one overrides any definitions of concentrations made in the added transport conditions. So whatever we fill in here, it will not be read. If we want to prescribe sediment concentrations, we simply switch off under physical parameters, morphology, the equilibrium sand concentration, and then it follows the prescribed concentrations. But we don't do that. We want to have that equilibrium. So that holds both for the upstream and for the downstream boundaries. As said, under physical parameters, we now not only have constant roughness and viscosity, we also have sediment. And in sediment, we can define the sediment properties. The specific density is rock, 2650, and the dry bed density is 1600, so that assumes a kind of porosity of 0.4, which is reasonable for sandy beds. The median sediment diameter, let's say that at 200 micrometers, and there is a bed layer thickness, an initial sediment layer thickness of 5 meters. So below the bathymetry, which is set at 5, we have 5 meters of sediment that can erode. Including sediments automatically adds morphology. The morphology will develop based on the gradients, the spatial gradients of sediment transport, and we will update the bathymetry during the run. We do that with the morphological scale factor of 100 to enhance the morphodynamic developments compared to the hydrodynamic timescales. And we have a spin-up interval before morphological changes of 720. That means the first 12 hours there is no bed level change. And we do that because if we spin up a model, you will see all kinds of disturbances of the hydrodynamics, sometimes with very large velocities, because it wants to find its equilibrium. And if you suddenly move the water, there's a lot of oscillations going on. Well, these oscillations are then associated with high gradients in velocities, and that may screw up your bed profiles and your morphological changes. So that's why we start the morphological changes only after the hydrodynamic spin-up has finished. With sediment and morphology, we have to save these files. I call it SO1, sediment, and morphology also SO1. I'm going to save other options. I save all files with the SO1 abbreviation. so that I know for sure that all my files with SO1 are related to my sediment transport conditions. So that created basically the more file and the set file. In the set file, we can open that and we really see the dry bed density, the initial sediment. That's all the things that we defined in the GUI. And under more, we find again all kinds of morphological parameters. I will come back to this later. Just let's run the model. I have quick plot already open, so I'm going to open the output files. To water level. I again have my output defined along the middle section of the stretch, and I'm going to add a blue line here. I pause a little bit and have some time to have the model propagate a little bit longer. So I took a small break, and the run is almost finished right now. So I can analyze the results. I'm first going to put my water levels. Let me finish this one. Along a transect called 6. Time point 1. This is my water level initially, and I add to that my bed level in black. Add the plot. To zoom in to make everything visible. Zoom out actually. And so this is really my initial condition. Now I'm going to make a movie, and I want to connect my water level to my bed level. So I switch on this V sign, and I say time, and it wants to link with the previous object. So the previous object is the bed level, and I want to link the bed level with the water level. I say yes. And then let's do the movie. You see that initially the water level gradients is set up, but then after 12 hours we allow for morphodynamic development. And you see that the bed level is now also starting to change. Maybe the figure is not very clear, so I stop this movie for this moment, and I'm going to analyze the bed level by itself over time. So the first 12 hours nothing happens, and then you see the lowering of the bed. See that the bed level at the landward boundary is kept at 5 meters, and it slowly evolves. It erodes all the sediment away, outside the domain, until finally a constant bed slope is met. And that constant bed slope is equal to the water level slope with a horizontal bed. So we are almost done here. If we go back to the plot of the water level and the bed level, I'm not sure if the plot is still open. Yes, it is. You see that this is the begin condition and this is the end condition, and both the water level slope and the bed level slope are the same. So there's a kind of, well, equilibrium depth or a flow depth that is constant along the model domain. We can take a look at it in cross section like this, but we can also take a view like this, where this is the bed level over time. Made a movie of that as well. Let's keep the limits, the color limits manual. So I put it at 4.5 and I put this at 6. Oops. Oh, wrong axis. Of course, this is a depth value, and depth values are negative here. So this is minus 4.5, and this is minus 6. Bed level values. So water depth values are always positive, and bed level values are negative. So initially everything at 5 meters, but then you see erosion. It takes a while, so I'm going to speed up. The way to speed this up is adding a value here separated by columns. It will speed it up by 6. So here you can see clearly that the bed level is eroding. It becomes deeper at the landward side. At the seaward side, what you also see is that there is no changes in, or hardly any changes in the cross sections themselves. It's a uniform development. There are some oscillations here, but it probably has to do, they're very minor. This probably has to do with very small numerical instabilities at the boundary. You can also take a look at the sediment transport. Let's analyze the history file for that. And that is the sediment transport here. We can separate between bed load. I'm going to do that mid-basin approximately. This is bed load, the black one, over time. So after a period of a couple of days where there's bed level adjustments, it remains constant. And I'm going to add there the suspended load. I'm going to add that to the plot. And you see, as expected, that the suspended load is much larger than the bed load. There's much more sediment transport in suspension than there is at the bed load. We can in the map file we can also put that in another perspective. We can make sediment bed load transport in a map file, not as vector but as magnitude here. And this is at the end, everything is constant, it's equilibrium conditions, but in the beginning it's slightly different. So this is some fun, but not very much fun. The reason is that we see a nicely uniform development of the bed level, but it would be fun to disturb the bed level a little bit. And I'm going to do that in the model domain, visualization area. And we did that before. I'm going to add some disturbances in the by means of a thin dam, for example. And I'm adding a thin dam here. To add that, and oops, is not the way. Yeah, if you don't draw it carefully, then oops, it doesn't want to do the way I want it to do it. I'm going to delete my thin dams. I'm drawing it again. Thin dam, add. I'm not sure why it wants to do it horizontally, so I'm doing it cell by cell now. That's completely filled. And here as well, that is better. So 2 thin dams. I'm closing here. I'm going to save all as, I call it SO2, SO2, SO2. I do that because I want to have the run settings different from the other runs that are in this working directory. An alternative way is to make another working directory if you do another run. So for each run that you do, you have a different working directory. You don't have to rename everything all over again. Okay, one other thing that we have to do right now is to change the bed slope effect. And we do that in the more file. So we open the more file in the text editor. You cannot do this in the user manual in the GUI, but the alpha BN is the bed slope effect. It is by default 1.5. Now 1.5 is nice if we use the Engel-Hansen transport formula, but we now use the Van Rijn formula, and then we should use an alpha BN of 50 approximately. So the transport bed gradient is basically the factor that determines how much sediment flows. It controls the amount of sediment that transports downhill. It's a bed slope effect, and it is associated with the bed slope transport. And a higher alpha BN results in more downhill bed slope transport. Bed sediment transport downhill. Yes. It's an important parameter to govern the meandering length of channels that we have. We'll take a look at that. Anyway, we are going to start this run. Called SO2. And it is running. I'll have a small break here for the run to finish. So the run has progressed now, and I'm going to look at the bed level in the water level points. Quick view on that. And indeed, we see in the beginning nothing is happening because of the hydrodynamic spin-up. But then after 12 hours, we immediately see that we have a lot of erosion at the narrow cross sections, and we have deposition towards the groins. And this is typically the real first morphological run that you are doing right now. And the longer it takes, the more stable the situation becomes. But you see this nicely meandering pattern evolving. Well, this is not really a nice plot. You can adjust the color map, for example, to Earth. It's a nice one. You can change from patches to continuous shades, and that gets much more nicer pictures here, as you will see. What you also see here is that the erosion hole here at the first groin is not deepening at a certain moment anymore. It's not deepening beyond 10 meters, and that's because we defined that under our bed level of -5 meters, there is only 5 meters of sediment available. If all that sediment is washed out, the bed becomes concrete and it cannot erode more than -10. And of course, you can adjust that, and you can say, for example, I want to have more erosion, or I want to allow more erosion. Another interesting exercise would be to change the alpha BN value in the MOR file. So this is the alpha BN value. You can put it to 5, you can put it to 50, you can put it to 100, and just explore what are the differences here. So play with the model, enjoy it, and I'm looking forward to seeing your results soon.